My dear friends, I am going to take the fourth lecture in Digital Logic family. I am Professor D.G. Trivedi and normally teaching digital electronics and electrodynamics. Dear friends, in this lecture, we are going to study about TTL parameters. What is TTL parameters? TTL parameters means floating input, then input voltages, output voltages, input current and output currents are called the TTL parameters. These parameters are measured under the worst conditions. Now the question is this, what is the worst condition means? Worst condition means these parameters are measured at temperature and different voltage range. Normally 7400 series, that is the commercial application of the TTL series, are working over a temperature range from 0 degrees Celsius to plus 70 degrees Celsius and a voltage range of plus 4.75 volt to plus 5.25 volt. That means 5 volt regulated power supply is required. Plus minus 0.25 volt variation is allowed. So this is your requirement of 7400 series. If you make a combination, that is minimum temperature and maximum voltage, or a maximum temperature and minimum voltage, or whatsoever combination which produce the worst values of the TTL parameter, that is known as worst condition for input and output voltages and currents. So this we have to study now, and to study these things we are going to study with the PPT. Now this is the lecture number 4. TTL parameters. 7400 series devices are guaranteed to work reliably over a temperature range of 0 degree to 70 degrees Celsius and over a supply range of 4.75 volt to 5.25 volt. In the discussion that follows, worst case means that the parameters input current, output voltage, input voltage, output currents and so on are measured under the worst conditions of temperature and voltage. This means maximum temperature and minimum voltage for some parameters, minimum temperature and maximum voltage for other parameter, or whatever combinations produce the worst values. The first parameters which we are going to study is called floating input. Now the question is this, what is the floating input? Floating input means the input is not connected anywhere. It is disconnected from rest of the circuit. Then it is called a floating input. When a TTL input is high, normally plus 5 volt, the emitter current is approximately 0, which will be shown in a figure 14.12a. When TTL input is floating or unconnected, as shown in a figure 14.12b, no emitter current is possible because of open circuit. Therefore, a floating TTL input is equivalent to a high input. Because of this, you sometimes see unused TTL inputs left unconnected, or an open input allows the rest of the gate to function properly. So if the floating input is unconnected, that means it is open circuit, and from base to emitter junction of the transistor Q1, current will be 0. Similar situation is going to be there. If the input is connected high, that is ideally 5 volt, then also base to emitter junction of the transistor Q1 is reverse bias and the base emitter current is going to be 0. And hence these two situations are considered to be equivalent and no current can flow. And that means if the TTL input is unused, or that means it is remains left to unconnected and it will work as a unused input normally. or floating. Now, there is another question. If you keep this TTL input unconnected or floating, is it any disadvantage? Yes, there is a disadvantage. What will be that disadvantage? When the input is floating, it will act like a small antenna and it will pick up stray electromagnetic noise voltages from the environment. Sometimes the environment is so noisy so that this signal will be so powerful that output of the gate will be changed without making any change of the real inputs. That means erratic operations is going to be occur because of this noise signals. So this has to be prevented, and to prevent this one, the unused input is normally not advised to left unconnected or floating, but it should be connected to either VCC or ground. Just I am reading the same thing over the PPT. There is a disadvantage of floating inputs. When you leave an input open, it acts as small antenna. Therefore, it will pick up a stray electromagnetic noise voltages. In some environments, the noise pickup is large enough to cause erratic operation of the logic circuits. For this reason, most designers prefer to connect TTL unused input to the supply voltage. For instance, figure 14.12c shows a 3-input NAND gate. The top input is unused, so it is connected to plus 5 volt. The same thing you can see in this 14.12 A, B, C and D figure. The first figure is this A, where the input of the transistor Q1, this is 4K and transistor Q1, input part of the TTL circuits, is connected with the plus 5 volt. That means it is connected with the high. Base emitter junction is reverse bias. No current will be there and the rest of the circuit will function properly. If the input is open, still there is base emitter junction is open circuit, current cannot be passed or it is going to be 0. These two situation of A and B is same, you can say that. The third figure C, this is a 3-input NAND gate. We require only 2-input NAND gate. So one of the input is extra. We can say that it is unused input. A and B is the real input. We are going to utilize we will convert this one into 2-input NAND gate. That means unused input should be connected to the plus 5 volt or directly, or it should be connected to the plus 5 volt with 1 kilo resistance. Now the question is this, what is the difference between these two? Here it is directly connected to the plus 5 volt unused input, and here it is connected through the pull-up resistance 1 kilo ohms to the plus 5 volt. A direct connection like this is alright with most Schottky devices, 74S and 74LS series. These two series which contains the Schottky diode, and hence they are having inbuilt protection against the noise, and that means if there is a spikes etc. is going to be there, it will not be harm to the gate which is having 74S or 74LS series. But if the old versions of the TTLs are there, that means 7400 standard TTL, 74L low power TTL and 74H00 series, that is high speed TTL, these are having input voltage rating of 5.5 volt. That means if the input voltage when it is in high state, if it exceeds 5.5 volt, it can damage this IC or a gate. And hence we have to see that the input voltage of this old TTLs should not be exceed 5.5 volt. What happens now? When you switch on the power supply, then there is a transient voltage is going to be generated, and that transient voltage will not be exactly 5 volt, but it will be higher than that, and then after it is going to be regulated. That means transient spike voltage which may be rise very fast and will be dying out very slowly. So there is a brief instant of time where the voltage is going to be more than 5 volt or 5.5 volt. And at that time, if it is passed through the pull-up resistance 1K for old devices, then what happens? The input capacitance of unused input of the TTL, which is going to be charged through the pull-up resistance, and the charging time will depend upon RC time constant. Now it will take time, and when it rises more than 5.5 volt, before that the spike has died out, and hence this gate are prevented from damage, and that's why this pull-up resistance are going to be utilized for 74, 74LS, 74L as well as 74H series. That means standard, low power and high speed TTL. This pull-up resistance is needed. But for this transient voltage, there is a built-in protection for Schottky and low power Schottky TTL, and hence we don't require pull-up resistance for 74S as well as 74LS series. They can be connected unused input directly to the VCC. Second questions, can we connect this unused input to the ground? Yes, if it is a NOR gate is there, the unused input should be connected to the ground. Otherwise, if it is connected to the VCC, then output will be stuck to the high in case of the NOR gate, and in case of this NAND gate, if this unused input is connected instead of plus 5 volt, it is connected to the ground, then one of the input is low, then output of the NAND gate is going to be definitely high. So it does not bother about A and B. So real inputs have no control over the output. It is stuck to the high. So this unused input in case of the NAND gate should be connected to the high state only or power supply only. Figure 14.12d shows an indirect connections to the supply through a resistance. This type of connection is used with the standard, low power and high speed TTL devices. These older TTL devices have an absolute maximum input rating of plus 5.5 volt. Beyond this level, the ICs may be damaged. The resistor is called a pull-up resistance because it serves to pull the input voltage up to the high level across the input capacitance. Most transient on the supply voltages are too short to charge the input capacitance through the pull-up resistor. Therefore, the input is protected against the temporary over voltages. Now, we will be talking about the worst case input voltage. Ideally, input can be connected low or high. Low means it corresponds to binary 0 and high means it corresponds to binary 1. Low stand for low voltage, that is called 0 voltage, and high stand for plus 5 volt. But in TTL, when it is taken from other logic circuits, then the input voltage may be different. Suppose there are so many gates which are going to be interconnected, and hence the output of any particular gate is connected as an input to another TTL gate, then the input voltage will not be the ideal values. So in a worst conditions, what are the input voltage which can be considered to be valid or which is going to be guaranteed, which gives the output is going to be particular depending upon input is going to be low or high. That we have to study here, and for that we will study with the TTL inverter. TTL inverter means we are going to have a circuit of TTL NOT gate. So if the TTL NAND gate is going to be converted into the TTL NOT gate by shorting these two inputs. That means the two input A and B is going to be shorted, and that means it becomes one input and it will work as a TTL inverter as shown in a figure 14.13a. Figure 14.13a shows a TTL inverter with an input voltage which is designated VI. I stand for input and O stand for output. So, and output voltage of V0 or VO, when Vi is equal to 0 volt grounded, it is in the low state and it is designated as VIL. VIL means input voltage when it is in the low state. With TTL devices, we can increase VIL up to a 0.8 volt and still have a low state input because the output remains in the high state. In other words, the low state input voltage VIL can have any value from 0 to 0.8 volt. TTL datasheets list the worst case low input as VIL maximum is equal to 0.8 volt. If the input voltage is greater than this, the output state is unpredictable. You can see that this is your TTL inverter circuit. The same thing, only one input and one output. This is a TTL NOT gate. So, if the input is designated Vi and output is designated V0. If the input is going to be low state, that means it is 0 volt is connected and hence the output is going to be in the high state. If the input is going to be 0, we designated VIL. This input from 0 volt we can increase a maximum up to 0.8 volt and still it will be considered as a low state input only because output remains to be high. Definitely it is guaranteed that it will remain into the high state only. But if you increase more than 0.8 volt, again the output voltage is unpredictable. And that's why the manufacturer or datasheet of TTL has given that VIL maximum is equal to 0.8 volt. Similarly, when the input is in high state, we designated VIH. That means input voltage when the input is in the high level, that should be plus 5 volt. That is ideal. But input cannot be plus 5 volt all the times. So, if the input voltage is lower than plus 5 volt, also it can be considered to be high state up to a certain particular minimum voltage. What is that minimum voltage? So, we can decrease the input voltage from 5 volt to up to a minimum of 2 volt, then also output remains to be low definitely. That means manufacturer can give the guarantee that even if you reduce the input voltage from 5 volt to up to a 2 volt in worst conditions, then also output is definitely remains to be low only. That means the input voltage is having a range for the valid high state is from 2 volt to 5 volt. So, this is the input characteristics, and this input characteristic of the TTL is known as a input profile. And in this input profile, each window, each rectangular box is known as a window. So, from 0 to 0.8 volt is known as a valid low state input. From 2 volt to 5 volt, it is valid high state input is there. If the input voltage is in between 0.8 volt to 2 volt, the output is unpredictable. Output is high also, it can be low also, we don't know. It depends upon the situation of the temperature and supply voltage and all that things. So, it is not a guaranteed that what will be the output will be there, and hence from 0.8 volt to 2 volt, it is known as a indeterminate value. Hence, output you cannot determine. So, this is regarding the input profile. Similarly, what should be the output? However, suppose Vi is equal to 5 volt in figure 14.13a. This is a high input and can be designated as VIH. This voltage can decrease all the way down to the 2 volt without changing the output state. In other words, the high state input voltage VIH is from 2 volt to 5 volt. Any input voltage in this range produce a low output voltage. Datasheets list the worst case high input as VIH minimum is equal to 2 volt. When the input voltage is less than this, the output state is again unpredictable. That means you can decrease the input voltage from 5 volt up to a 2 volt. That 2 volt is a VIH minimum. For that, the output is definitely remains into the low state. When the input is less than 2 volt, then output is unpredictable. Figure 14.13b summarize these ideas. As you see, any input voltage is less than 0.8 volt is a valid low state input. Any input greater than 2 volt is a valid high state input. Any input between 0.8 to 2 volt is indeterminate because there is no guarantee that it will produce the correct output voltage. Now we will talk about the output voltage in the worst case conditions. Ideally, the low output state is 0 volt and high output state is going to be plus 5 volt. We cannot attain these ideal values because of internal voltage drop inside the TTL devices. For instance, when the output voltage is low, in figure 14.13a, Q4 is saturated and has a small voltage drop across it. Normally, you know that when the transistor is in a saturation, that means the voltage drop between the collector and emitter is approximately 0.2 volt. That means with TTL devices, any output voltage from 0 to 0.4 volt is considered a low output and is designated as VOL. VOL means output voltage when the output is in a low state, valid low state. It is the range from 0 to 0.4 volt. This means the low state output VOL of a TTL device may have any value between 0.0 and 0.4 volt. Datasheet lists the worst case low output as VOL maximum is equal to 0.4 volt. When the output is high, Q3 acts as emitter follower. Because of voltage drop across Q3, D1, diode and 130 ohms resistance, the output voltage will be less than supply voltage. With TTL devices, the high state output voltage is designated as the VOH. VOH means the output voltage when the output is in the high state. And this output voltage, ideally it is required to be plus 5 volt. But we know that output is not going to be 5 volt because output is taken from emitter follower and there is that transistor Q3 of the totem power arrangement is going to be conducting. And hence there is a voltage drop across 130 ohms, there is a voltage drop across collector and emitter of the Q3 and there is a voltage drop across diode D1. Hence the voltage is going to be changing and at the cathode of the D1 or output voltage Y is going to be less than 5 volt. Normally it is in the range from 2.4 volt to 3.9 volt depending on the supply voltage, temperature and load. Datasheet TTL datasheets list the worst case high output as VOH minimum is equal to 2.4 volt. Figure 14.13c summarize the output state. So, if you see the output profile, this is your TTL output profile, figure C. Here also this is called output characteristic or output profile. There is a low window from 0 to 0.4 volt is considered to be very low output. From 0.4 to 2.4 is considered to be indeterminate window and from 2.4 to 5 volt is considered to be valid high state output. Here there is a printing mistake, it should be valid high output. So, if the voltage of the output is less than 0.4 volt, it is considered to be valid high output. And if the input voltage is greater than 2 volt, then it is valid high state output up to 5 volt. Profile and window. The input characteristic of figure 14.13b are called the TTL input profile. Furthermore, each rectangular area in figure 14.13b can be thought of as a window. There is a low window which is normally from 0 to 0.8 volt, an indeterminate window that is 0.8 to 2 volt, and high window is from 2 volt to 5 volt. Similarly, figure 14.13c is the TTL output profile. Here you see a low window is from 0 to 0.4 volt and indeterminate window is from 0.4 volt to 2.4 volt and high window is from 2.4 volt to 5 volt. Now, when we deal with the TTLs, we have to remember these values for valid low state input, valid high state input, indeterminate state input profile as well as output profile. We have discussed the low and high state for the input and output voltages. Here they are again as a reference for the future discussion. VIL maximum is equal to 0.8 volt, VIH minimum is equal to 2 volt. That means any voltage maximum up to 0.8 volt can be considered as valid low state input, and any voltage which is going to be up to 2 volt is considered to be valid high state input. Similarly, VOL maximum is equal to 0.4 volt and VOH minimum is equal to 2.4 volt. That means if the input output voltage is lower than 0.4 volt, it is considered to be valid low state output, and if it is greater than 2.4 up to 5 volt, it is considered to be valid high state output voltage. These are the worst case values shown in a figure 14.13b and c. That means in the worst condition, this values range can be obtained. On the input side, a voltage has to be less than 0.8 volt to qualify it as a low state input, and it must be more than 2 volt to be considered as a high state input. On the output side, the voltage has to be less than 0.4 volt to be low state output and more than 2.4 volt to be high state output. Next important things is compatibility. What is the meaning of compatibility? Compatibility means output of any TTL device is connected to the input of any other TTL device. Can we connect directly without any buffer stage or anything else? Then it is called compatible. That means the output of a previous device should be compatible with the input of next device. The previous device which is driving the next device is called TTL driver, and it is output of this device is connected to the input of the TTL device, which is known as a TTL load. That means how we can check this compatibility. To check this compatibility, we have to see the input TTL and input output profile. Windows. Output windows of the TTL, that is from 0 to 0.4 volt, is fit inside the TTL input window of 0 to 0.8 volt of low state. Similarly, output window from 2.5 to 2.4 volt to 5 volt is fit inside the input window of 2 volt to 5 volt when it is in the high state. So, the output windows are fit inside the TTL input window, and hence we can say that they have the compatibility. TTL devices are compatible because low and high output windows fit inside low and high input windows. Therefore, the output of any TTL device is suitable for driving the input of another TTL device. For instance, figure 1414a shows one TTL device driving another one. The first device is called the driver and second device is known as the load. Figure 1414b shows the output stage of the TTL driver connected to the input stage of a TTL load. The driver output is shown in the low state. Since any input voltage less than 0.8 volt is a valid low state input, the driver output in a worst conditions is in the range from 0 to 0.4 volt is compatible with the load input requirements. Similarly, figure 1414c shows a high TTL output. The driver output is from 2.4 volt to 3.9 volt, which is compatible with the load input requirement, which must be greater than 2 volt. So you can see this figure. The first device, which is known as a TTL driver, the second device, which is called TTL load. They are interconnected by simple wire. So output of the TTL device is connected to the input of TTL load. V0 is taken as a Vi for the TTL load. The same thing is going to be shown here in a schematic circuit diagram. The first in a circuit B, you can see that this is the totem pole arrangement of the TTL driver. 130 ohms, Q3 transistor, diode D1 and Q4. Q3 and Q4 forms totem pole arrangement, and this point is the output of TTL driver, which is connected to the TTL input circuit, that is TTL load. What is the input circuit? 4 kilo ohms resistance and transistor Q1 is there. So this point is the input. So output of this one is directly connected to the input, you can say that. Now, when the output is in the low state, definitely in the worst case condition also, it will be in the range from 0 to 0.4 volt. Then and then only it is considered to be valid low state output. And the input requirements of this TTL load is less than 0.8 volt. So it is definitely less than 8 volt, and hence it is compatible when the output is in a low state. Similarly, in this figure C, same circuit is there, but we are checking here the compatibility for high state. When the output of this TTL driver is going to be high, it will be normally in the range from 2.4 volt to 3.9 volt, and that output is directly connected to the input of TTL load. The input TTL load minimum it requires 2 volt. So in between 2 volt to 5 volt, it will be definitely considered as a valid low state, a valid high state input. So the output of the TTL driver, which is greater than 2.4 volts, is definitely considered as a valid high state input for the TTL load. So there is a compatibility for TTL driver and load or TTL circuit in a high state also as well as in the low state also. So this is known as a compatibility. Second important things, we have studied there are different type of the TTLs. Standard TTL, then high speed TTL, then low power TTL, then Schottky TTL and low power Schottky TTL. All type of the TTL, the input profile and output profile for the voltages for the low level and high level and indeterminate state, it is going to be the same. And hence, out of this 5 type of the TTL, any type of the TTL you can utilize as a driver, and any type of the TTL you can utilize as a load. So there is no problem. Any one type of the TTL, either it is going to be standard, low power, high speed, Schottky TTL or LS can be utilized as a driver, and any other type of the TTL you can utilize as a load. Only their currents are different. That means how many number of output inputs you can connect to this output, that is going to be different. That is going to be vary, and that is known as the fan-out capability that we are going to see after in a second lecture. Okay, friends, thank you very much.